The potential difference, delta V, between the two charged spheres in this problem is 500 volts, and we're asked in part A to find the charge Q on the inner sphere. We'll do this using this expression for the potential difference. It equals the line integral from the inner sphere to the outer sphere of E dot dr. Because the potential reference is arbitrary, we can set the potential equal to 0 on the outer sphere, and then write down expressions for the electric field. We know from Gauss's law that the electric field is 0 inside the inner sphere and outside the outer sphere. In between the two spheres, the electric field is radial, and it has a magnitude 1 over 4 pi epsilon naught Q over r squared. If we substitute this electric field into the integral above and integrate, we find that delta V, the potential difference, equals Q over 4 pi epsilon naught 1 over r1 minus 1 over r2. Solving this expression for the charge Q gives us this result, into which we can substitute all the known values. 4 pi epsilon naught is 1 over the Coulomb constant, which I'll write here. We know the potential difference, delta V, is 500 volts. And we know R1 and R2, so we can evaluate this quantity in parentheses. Multiplying those three values together gives us the charge Q of 7.62 times 10 to the minus 10 coulombs. That's the answer to part A. I'll move it up here so that we can keep track of it, and begin solving part B, which asks us to draw equipotential surfaces corresponding to several different voltages. To do this, we can first notice from our previous expression for delta V that the potential difference at any distance r can be rewritten like this, by replacing r1 with the variable little r, valid in between the two spheres. Now let me erase all of this and move this expression up to the top so we have room to work with it. We can solve this expression for 1 over r, 1 over the distance at which a particular potential occurs. We know the values of 1 over the Coulomb constant in the charge Q, and we know the value of 1 over r2. So if we're now given a potential difference, delta V, we can find the radius r where the equipotential surface occurs. If we put 500 volts for delta V, we find that the radius equals 1.20 centimeters. It's the inner sphere. And that looks like this. Substituting 400 volts for delta V gives us this radius. And I'll draw that here. 300 volts gives us this radius with a slightly larger gap from the second one. Substituting delta V is 200 volts gives us R2 equal to 2.53 centimeters. And that looks about like this with increasing gap size. 100 volts gives us an equipotential surface radius of 4 centimeters, looking like this. And finally, at 0 volts, the equipotential surface occurs at a radius of 9.60 centimeters on the outer sphere, as expected.